Welcome to today's video. Today we're going to talk about black holes, and in particular we're going to talk about Schwarzschild black holes, which are the simplest kinds of black holes. Then at the end of the video I may say a little bit about complications, but understanding already Schwarzschild black holes a little bit would be quite a feat. So we're going to focus on that. There is a number of things that people in popular culture kind of know about black holes. There are some others that people have as misconceptions. We're gonna deal with them, and we're gonna talk about hopefully all the most popular ones and the ones that are misconceptions, and we're gonna try to understand first from the perspective of what we already know, and then we're gonna start discovering new things about it. We will try to discuss what is the experience like for somebody who'd be falling into a Schwarzschild black hole, which is nothing like popular culture usually portrays it. Above all, if you fall into a big black hole, if it's really large, like galactic center kind of black hole, then it would not spaghettify you before crossing the horizon. You can cross the horizon no problem and things like that. We will talk about all this, but to begin with, we're gonna start analyzing the scenario of a Schwarzschild black hole without really like doing the typical calculations that people will do even in first year undergrad if they do this in a course to Introduction to Modern Physics. We're going to start from there, and we're going to be going to understanding more now because we know general relativity a little bit better than back then. We're going to understand a little bit more this time. All right, let's get to it. So first of all, we're going to consider a space-time that is generated by some distribution of stress energy, so that the distribution of stress energy is concentrated under the Schwarzschild radius.
Before continuing, I think it's important to give a little bit of context on when, in the realistic astrophysical context, we would expect to find these kind of monsters. So there are three typical sources of astrophysical black holes. The first source is the final stages of a star that is massive enough. Stars are stable because there's a competition between the pressure that is generated through nuclear fusion and a gravitational pull that tends to get all the matter in the star together. Now, when the nuclear fusion at a star ends, for whatever reason, it could be because it reached some material that is stable enough that cannot be fused again. So in that case, we get that the star will contract. The gravitational pull keeps contracting the star, and there's nothing that prevents it from contracting. Now, at some point, what would happen is that the matter in the star is so close that the electron gases surrounding all the atoms are so close to each other that trying to put, a little bit hand-wavily, trying to put electrons all together is not possible because electrons are fermions and they don't want to be on the same state. So when we try to contract them, we're reducing the volume or the phase space, and it appears what we call degeneration pressure. And that degeneration pressure of trying to compress too much the volume of the phase space of those electrons, may stop the contraction, the gravitational contraction, if the mass of the star is not too much. If that happens, we end up with a white dwarf. Now, it could happen that the star still is too massive and it's impossible to contain with electronic degeneracy pressure to contain the contraction of the star, and if that's the case, then the thing is overcome, and what happens is that electrons are produced in a way, the plasma that makes the star is pushed together way more, and you start getting processes where the electrons react with the protons, if you want, and create more neutrons. And that is a very well understood process. Now, if that were to happen, eventually you get a star that is dominated. There's a lot of neutrons. It behaves like a huge, kind of a huge atomic nucleus in a way. Also, the shock waves of the contraction, because the matter is falling too fast, can create a supernova. So in any case, the remnants of that supernova, having a plasma dominated by neutrons, may stop the contraction because, again, neutrons are also fermions. They don't want to be put together and compressed in their phase space. Or it could happen that still the remnants is too massive and the collapse would contract. The shock wave of the supernova would be even larger. But in that case, what we would have is that the neutrons would start bosonizing. It would form collective excitations, taking several neutrons and making them bosons. Then nothing stops the contraction, nothing that we know of stops the contraction, and the contraction can get the matter to contract below the Schwarzschild radius, or the equivalent radius if we have angular momentum. So that's what actually would form an astrophysical black hole out of a star. There are other kinds of astrophysical black holes. Those ones that I talked about typically have of the order of 1 to 10 of solar masses. But then we have the black holes that are at galactic centers. Those are of order of millions of solar masses. They are primordial in the sense that they were formed at the same time that the galactic structure was formed. And I'm not going to talk much about them, but we can. Those are the most boring black holes, but also the most traversable black holes. Finally, as we will discuss in the video, of course, and finally, we would have some intermediate regimes black holes that are formed through coalescence of several black holes, so collisions between black holes and other similar phenomena. Those are the ones that we have been able to observe recently through the Gravitational Wave Observatory at LIGO. Anyway, so this is how black holes appear in the wild, and with this, we're going to go back to the video and analyze the particular case of Schwarzschild black holes that we have in this course.
And that's a bit of a problem, because you see here that the Schwarzschild space-time that I wrote here, the Schwarzschild metric or line element rather, that I wrote here, has two problems. It's got a problem, or two apparent problems at least. They look like problems. We'll see if they are. One is at r equals the Schwarzschild radius, and another one is when r is equal to 0. When r is equal to 0, this explodes and this thing breaks. And when r is equal to rs, this thing breaks and the thing explodes. So there seem to be problems at r equal to 0 and r equal to Schwarzschild radius. All right, before we get into analyzing those problems and if they're really problems or what they really are, let's discuss an approach to analyzing what happens in the fall into a black hole that consists of computing how long does it take to fall into a black hole, kind of thing. So to do that, we're going to consider three observers here. We have Bob is at infinity, then you have Alice, that for simplicity, Alice, we're going to drop her at infinity. We're going to like push her a little bit, and she's going to fall to the black hole from infinity. Then we have here Carol, that is stationary with propulsion at some radius, r equals rc, and then there's Schwarzschild radius. And we're going to ask the question, Alice is falling. At some point, Alice passes Carol. How long is it going to take from Carol to the Schwarzschild radius? For Alice to go from Carol to the Schwarzschild radius. How long is it going to take as seen by Bob? How long is it going to take as seen by Alice? Okay? And we're going to compare and discuss a little bit what the results are. Now, we can do this calculation because we know orbital mechanics. And this is all geodesic. This is an orbit. Well, it's free fall, right? It's a collision orbit, but an orbit nevertheless. All right, so let's see what we have. First of all, let's consider the for velocity for Alice and the normalization condition. So we have the normalization condition. The for velocity of Alice squared, if you want, is -1 because it's a time-like trajectory. And we know that that means this. Why do I know that? Well, let me just quickly remind you. The for velocity of Alice is going to be t dot, r dot, theta dot, phi dot, right? And we know, of course, that Alice is, in this case, is going to be falling radially, just free falling from infinity towards the center. And that means that there's going to be a t dot, there's going to be an r dot. Of course, remember the dot means derivative with respect to her proper time. So because we parameterize this trajectory with respect to proper time, and there's no angular variation anywhere because it's a radial infalling trajectory. Now, of course, I compute u mu as the contraction with the metric of u mu, right? And then only these two terms will be non-zero, which is the two that I wrote here. And this is the coefficient 0, 0 of the metric, that is right here, and the coefficient 1, 1 of the metric, or r of the metric, that is this one here. All right, we also have the conserved quantity k mu v mu. Remember that for this space-time, we know that t is a cyclic coordinate. Therefore, we know that there's a Killing vector field k that is partial t, right? If I represent it in the coordinate basis associated with t, r, theta, phi, that vector would be, let me represent it like that if you want, that's going to be the vector 1, 0, 0, 0. So I know that the contraction with of k with the for velocity of Alice, because the for velocity, I wrote here v, but let me write u because it's the one I use for the for velocity of Alice. The for velocity of Alice contracted with this vector will give me, well, again, this is the same. If I write it here, this is the same as g mu nu, u mu, k nu, right? And of course, it's only one component, that is with t, and the 0 and the tt component of the metric, which is this one. And that's what gives me this conserved quantity, which is what we've been doing in the previous video as well. All right, so we got those equations. Let me clean all the explanations. All right, so I numbered these equations. I numbered 1 and 2. So what I do here, I substitute the conserved quantity 2, if you want, into equation 1, and I get this. And now what I want to do is to determine the value of this conserved quantity for the particular case of Alice. So for simplicity, let's consider that Alice, so let's say, let's find E for Alice's fall. Alice's fall. All right. So what do we know about Alice's fall? Well, we know that she's free falling from infinity. So at infinity, Alice starts out in the radial direction with 0 speed. It's just starting to fall, just a notch with 0 speed, like starting to fall, slightly away from the stationary region. Okay, so using that, all right, let's find the value of the conserved quantity E. that will allow us to solve the problem. Now, we want to find the conserved quantity E for Alice's fall. Let's say that Alice, I know that I want to take Alice to fall from far away, but to begin with, let's say that Alice is released, so she's being held by a stationary platform that has propulsion there to stay stationary, and a radius r equals r0. And suddenly that releases her with no speed, it just releases her. So if they do that, at time equals t0, Alice starts falling towards the center, right? Now, that means that the initial position is r0 at time t0, and also that she starts with no speed. Let's write those conditions mathematically. Gives me the set of equations 3. So r of t0 is r0, r dot of t0 is equal to 0, which I can substitute in this equation, and then this disappears, and this becomes an r0, and that gives me the value of the conserved quantity E squared, right, for Alice falling from a point r sub 0. Now, of course, that means that E, if you want, it's equal to plus minus square root of 1 minus rs divided by r0. I could pick, it's like both are a conserved quantity, right? A conserved quantity and a minus conserved quantity are the same. We have to pick the branch that is most convenient for us when we want to do it. Now, again, now say that Alice falls from far away, a little bit closer from Bob, so it's feeling the field, but it's kind of really far away. So we can take the case of Alice starting from far away, just to simplify the calculation. If r0 goes to infinity, then we know that the conserved quantity E is equal to plus minus 1. All right, wonderful. Now, knowing that, we can do the following. That is, okay, I name this equation 4, substitute the value of E squared equals 1 in this case. In 4, we get this equation, and then take the square roots, and then r dot from this equation is minus the square root of rs over r. We notice that I picked the negative branch of the square root here. Why? Because the trajectory of Alice is in falling. The trajectory of Alice being in falling means that as time passes, radius decreases. So I want a negative derivative of r with respect to proper time of Alice. All right, wonderful. Now, the next step is integrate that equation. If we want to find out how long does it take to fall from Carol, so Alice will be falling, at some point reach Carol. How long does it take to fall from Carol to the Schwarzschild radius, as seen by Bob and as seen by Alice? Let's do that calculation. So how long does it take for Alice to fall from RC to RS? Well, from the point of view of Alice, according to Alice, in how long, according to Alice's watch, Alice's proper time does it take, then it's not too difficult because it's just integrated the differential of proper time from the 2 points, right? And then we know that that differential of proper time I can write as, this is, if you want, this thing here is d tau, right? So I can integrate this dr, d tau dr, and d tau dr is nothing but the inverse of this thing, is the inverse of the velocity. This is dr d tau. All right, so I substitute by the inverse and integrate, and I obtain this, which you can tell the amount of time depends on how large RC is and how large the Schwarzschild radius is, right? And this is the amount of time. Now, of course, this is clearly a number. This is, let me just simplify it like that. This is less than infinity. It's a convergent number. It's a finite amount of time. It takes Alice a finite amount of time to fall from Carol to the Schwarzschild radius. All right, wonderful. Now, let's do the same computation, but according to Bob. How long does it take for Alice to fall from Carol to the Schwarzschild radius as Bob would measure? Now, for that, we need to do a little calculation first. In order to compute the amount of time that it takes for Alice to go from Carol to the Schwarzschild radius from the point of view of Bob, then we start from here. We start from this expression that I have here. What is that expression? So I have expression for t dot. What is the derivative of t with respect to Alice's proper time? Where did I get this from? Here. I just solve for t dot in this equation here, right? So what I get is this expression. And the nice thing is that r dot, so dr d tau, I know what it is because I already computed what r dot is for this for Alice's fold. Wonderful. So I substitute that, and then I simplify the whole thing, and the whole thing actually simplifies to this expression here. The common denominator for these two, and you'll see you get 1 minus rs over r plus rs over r, so the rs over r in the numerator cancels, and then you get 1 over, you basically get the sum of these two things is nothing but just this factor that you can take the square root of, and it's 1 minus rs over r to the minus 1. All right, so that's the relationship. Let me just write it here. This thing is tau dot, so that means is t dot, sorry, so dt d tau. Okay, now with that, we can compute dr dt, right, which is what we need to integrate in order to find what we want. The same way, well, actually the inverse of that, we need to compute the integral of. Okay, but this, using chain rule, this thing is dr d tau dt. Wonderful. So I substitute dr d tau, I already have, is this thing here. So this is minus square root of rs divided by r, okay, multiplied by d tau dt, which is the inverse of that. 1 minus rs over r to the 1. All right, well, knowing this now, the next step is integration. So this integral, integration, like this, and we have the delta t, of course, is the integral of dt, which is dr dt dr, as I have here, from rc to rs. If I substitute dt dr is the inverse of this thing that I found, I get this integral here. Now, what is this value? You can tell that something weird is going on here, because at the limit rs, this integral is going to be divergent, and in fact, the integral, it's going to go to infinity, as the final point is made go towards the Schwarzschild radius. Now, look at this. This is the first thing to think about. Alice takes a finite amount of time, according to her, with her watch, from going from Carol to the Schwarzschild radius. But Bob sees that Alice takes an infinite amount of time. In fact, Bob would see how Alice is falling towards the horizon, towards the Schwarzschild radius. I haven't even talked about horizon yet, towards the Schwarzschild radius. And when she's really, really close to the Schwarzschild radius, Bob starts seeing how she's going slower and slower and slower and slower and slower, and eventually kind of freezes very close to the Schwarzschild radius and remains there. In fact, of course, because there's a redshift factor, Bob will start seeing Alice go, the light coming from Alice would be redder and redder and redder, and therefore Alice would kind of become like, go towards the infrared and so on, eventually become invisible. But it will take an eternity, literally an eternity, for Bob to see Alice fall into a Schwarzschild black hole. Alice, however, only sees a finite amount of time going in. So this is striking. This is very striking. Something that takes a finite amount of time for somebody, it takes an infinite amount of time for someone else. And it's not just Bob. You can do the similar calculation. It's just less glamorous if you want, but you can do it. It's very doable. And if you want to do it for practice, do it. The amount of time that it takes for Alice to fall from Carol to the Schwarzschild radius, as seen from Carol, is also infinite. Whereas for Alice, is finite. So everybody outside or far away from the Schwarzschild radius would see Alice taking forever to fall. Whereas for Alice, it just takes a finite amount of time. He says, oh, yeah, I crossed. We will see, we'll talk more about what it means to say I crossed and what the experience of Alice would be. But this is remarkable, right? There is a kind of an infinite difference in time, an infinite redshift factor as Alice gets closer to the horizon. This is something that is kind of known in popular culture, but you're sitting now with a calculation, with orbital mechanics. All right. This is interesting. So there's something with this R equals Rs. Is this a real problem? So what's going on at R equals Rs? We need to understand these two apparent singularities that we have here. One when R is equal to Rs, and one when R is equal to 0. We need to understand it because this is physically strange. Physics predict this. It's something that is predicted, but it's weird. So let's try to understand better what happens close to the horizon and what happens also with the other point where this thing seems to be singular, or at least apparently singular. Alright, so the first step to understanding what happens at points r equals rs and r equals 0 is to try to see, we can wonder the following. Look, okay, so something happened as R equals Rs. But is this a problem of the space-time, or is it a problem of the humans that are trying to understand that space-time? Because it could perfectly well be the humans. Problems that humans have with coordinates. We have, some point in the sphere, there's a radial coordinate R. Let me draw some axes here, like this, and imagine that this thing and like that, and imagine this thing projects like this. So you have a polar coordinate, theta, and then you also have an azimuthal coordinate, phi. Now, of course, we can wonder, what are the coordinates of the North Pole? Well, the coordinates of the North Pole are ill-defined. At the North Pole, theta is 0, but phi could be anything. It's ill-defined. So it's not that the North Pole doesn't exist or it's a bad point or whatever. It is a point. It's just that your choice of coordinates is bad if you want to describe that point. You chose the wrong coordinates. You need, remember, for a sphere, I need at least 2 charts to have an atlas, right? A smooth atlas. And that's because if any atlas that I would pick, I mean, it's related to the fact that this is a compact manifold sphere, but I'm not going to get into that. You can ask about that in the live sessions. But you see that I need at least 2 sets of coordinates to displace a little bit the North Pole to be able to describe the North Pole. These coordinates, spherical coordinates that I wrote here, would never describe the North Pole. So, is that what we have? It is a human problem. This is us choosing the wrong coordinates to describe that point. Is that what's going on here? Well, I don't know. Let's see. Let's compute. So one thing that we can do is compute a scalar. Why? Because scalar fields their value are coordinate independent. They have no indices, scalars, and therefore they transform with the identity. They don't transform, they remain invariant under changes of coordinates. So something whose result is coordinate independent. So using these coordinates, right, t, r, theta, phi, let's compute the Kretschmann scalar. This is a scalar I haven't talked about. We could have computed the Ricci scalar, but I thought maybe the Kretschmann scalar is better for this case. So now you know another scalar that has a name, another scalar field that has a name. This one is the full contraction of the Riemann tensor with itself. Okay, so you can compute it. You can do it by hand with this metric. If you're in my course, you will do it by hand, or at least some of them, in an assignment, computing all the coefficients of the connection, all the Christoffel symbols, all the Riemann, the components of the Riemann tensor, the components of the Ricci, etc., etc. You can use the mathematical notebook I have on my website to compute it if you want. In any case, this scalar, if you compute it either by hand or whichever other means, it's a long calculation for sure. I'm not going to do it here, it's really, really long. But what it gives you is 12 times the Schwarzschild radius squared divided by r to the power of 6. Ha! What does that mean? Well, that means that at r equals rs, this thing is finite. There's no problem. It's smooth. I can pass that point, the horizon, if you want to call it that, even though I haven't given you a reason yet to call it horizon. But you can cross that point. You can cross the Schwarzschild radius, and the Kretschmann scalar says, I'm fine, I'm okay, nothing happens here. So, the problem at r equals rs is not really a singularity, a real singularity. It's actually a singularity just because of the choice of coordinates that I picked. I picked my coordinates wrong if I was planning to describe that point. In fact, there are systems of coordinates, of course, where the metric is not singular at the horizon. I can change to another system of coordinates. For example, this one, like this one. This is the Kruskal-Sekeres coordinates, and this is just a set of coordinates defined like this in terms of, in particular, they have the same angular coordinates, theta and phi, but I make a substitution of t and r with this new variable capital T and x. And of course, when I see an r, I have to substitute r by r of t and x. And r of t and x is actually defined through this implicit relation that you see here. Now, this is not an easy change of coordinates if you haven't seen anything like that before, but the important bit is that if you actually use these coordinates for the Schwarzschild spacetime, so if you do a change of coordinates on the metric, you get that the line element looks like this. And this is capital T. And the line element like this, you can tell already that at the horizon, at r equals rs, nothing happens. Nothing special. The coordinates don't cancel, nothing goes to infinity. So certainly the problem is, or the problem was, that we picked the wrong set of coordinates if we wanted to describe things that are going to cross the horizon. Now, Very interestingly, of course, you have to make a choice. That's the thing. It's like with the sphere, with the North Pole and so on. These ones don't work really well for points at infinity. For that, it's much better to use these coordinates, these Schwarzschild coordinates like this, t, r, theta, phi. Now, of course, so this is just to illustrate that there are indeed systems of coordinates or coordinates that will make the point r equals rs not special. Well, rather than not special, more like not sick, if you want. Now, I think now that we understand that that point is okay, the problem was the coordinates, we can wonder two things. What truly happens then at the horizon? What would happen if I cross the horizon? What's going on there? That's gonna be one thing we're gonna answer. But before that, we have the other question. What happens at r equals 0? Now, at r equals 0, we do have a problem. The curvature scalars do diverge. You have a point of infinite curvature. This is a point where the theory breaks. And indeed, this is problematic. There's something, the singularity, we call that actually the singularity of this space-time. And that point really is problematic, a point of infinite curvature. Basically, at that point, our theory can never be able to describe what's going on. In fact, having singularities is really tough. Luckily, there's, as we will see, we will talk a little bit about it, an event horizon. But indeed, what happens at r equals 0 is that the solution to the equations break down. We can actually play as if it were real, because probably it still works pretty well up to very close to the horizon based on our current experimental understanding. But at the horizon, the theory would break down. It's kind of nice because relativity tells you, dude, I can only tell you up to so much. After past this point, maybe be careful and find something else. So that's the case around r equals 0 here. But let's try to understand better what this thing is, this singularity, and how trajectories would move in a Schwarzschild background, and in particular, what happens when you cross a horizon. Let's see it. All right, we're very close to understanding a little bit better what happens at the r equals rs, at the Schwarzschild radius for a Schwarzschild black hole. Now, let's analyze two vectors that are very important. Those are the vectors that mark the radial direction and the time direction. So, the radial direction tells you, you see a Schwarzschild black hole, you can point, you're looking from the outside at a Schwarzschild black hole and you say that, oh, there's the center. You can point at the center of the black hole. The center, that direction, the radial direction, like this. It's a spatial direction. You can point at it, right? The radial direction of all the possible directions, the radial direction is that one, the one that points at the center of the black hole. All right? Now, what about the vector in the direction of time? I call it k because that's the name I gave it for symmetries, because it's the killing vector k here. Anyway, the vector in the direction of time, that tells you what does it mean to move to the future, to the past. It's not a direction in space, it's a direction in time. If you have these coordinates, t, r, theta, phi, you cannot point at t, right? T is kind of, we can point at your watch. It's a vector pointing towards the future, right? Okay. Now, as such, let's analyze the norm of them. The norm, of course, if it is marking a spatial direction, it has to be a space-like vector, whereas the one marking a time-like direction has to be a time-like vector. Okay, so let's compute the norm of the both vectors, right? So that means that r mu, which is of course g mu nu, r mu, r nu. What is that? Well, this vector only has r component, so it's g r r r r r r. It sounds like a pirate. Anyway, so this g r r is this factor here. So this is equal to 1 minus rs divided by r to the minus 1. All right, and then it's 1 and 1, so I don't write the ones. That's the factor. All right. Now, how about k? Well, with k, we get k mu, and that is g mu nu, k mu, k nu. And of course, this one only has temporal component, so this is gtt, kt, kt, and gtt is this factor, so minus 1 minus rs, r, and that's it. Kt is 1. All right, so let's analyze that. When you are outside of the horizon, so you're at a radial coordinate larger than rs, so for r larger than rs, let's have it a table like, right? Like this. We're gonna have an r smaller than rs. For r larger than rs, this thing is right. So this thing is smaller than 1, therefore it's 1 minus something. This thing is positive. So r mu is positive. What about k? Well, k mu is minus 1 minus something smaller than 1. So this is negative. Which makes sense because this is a space-like vector, right? And this is a time-like vector. So indeed, the coordinate t, which is time for somebody in infinity, is a direction in time. Whereas the coordinate r is a direction in space, that direction, pointing to the black hole, right? All right, but what happens inside the surface r less than rs? Well, look at that. So if this is the case, if r is smaller than rs, then this thing is larger than 1. Therefore 1 minus something larger than 1, that makes r mu negative. And that makes k mu positive. What? This vector is time-like now. And this vector is space-like now. Wow. So, no, seriously, wow. What happened here? So this is interesting. What happens is that as you get closer to the Schwarzschild radius, what you get is that the character of r and t swaps. It's like, remember that when you start doing Lorentz transform and the axes suddenly go like this? Well, imagine that they are allowed to continue and invert themselves, because that's what's going on here. So this is very weird. So let's analyze what's going on. Outside of the black hole, the radial direction is a direction in space. That makes sense. You can point to the singularity because it's somewhere in space. It's over there. It's inside the black hole, over there. R equals 0 is this direction. When you are outside of the black hole, partial t is pointing in the direction of time. Counting t is counting time. However, when you're inside, where is that? R is no longer a direction in space. It's a direction in time. That is very interesting because that means that once you cross, many people imagine falling into a black hole and crossing the horizon, or crossing the Schwarzschild radius, we haven't called it horizon yet, crossing that surface, and then suddenly, there's so much gravity, the singularity is attracting me so strongly, singularity over there, that no matter how strongly I activate my thrusters, I'm not going to be able to escape because the gravitational pull is so hard. That's not it. That is not it. If you cross the horizon, what would happen is what you call, at infinity, you call the radial direction, the direction in which you will face the singularity, now it's a direction in time. I cannot point at the singularity anymore. I can't. I've lost the ability to point at the singularity because the singularity is in a direction in time. So in a plane of simultaneity of mind, the singularity is nowhere to be found. The singularity, when I was outside, was there. But once I cross the horizon, it's not anywhere in the room. It's in the future. And the reason you can't avoid it, the reason you can't avoid the singularity is because it will happen in the future. It's in your future. It's in your freaking destiny. And in fact, it's in the destiny of every freaking body that crosses the surface of the Schwarzschild radius. And this is a weird surface also, but so what does that mean really? Well, it means that after you cross, you will not see a point in space attracting you very strongly. That point is now in the future. You will not see it anywhere. You will hit it eventually in the future because all trajectories inside the black hole, inside the horizon, will actually hit that singularity. And we will talk about that. We will talk about that because that's what justifies us to call the Schwarzschild radius coordinates a horizon. And we will talk about that. But it is really interesting because, again, it's not that you can't avoid the singularity because it's attracting you. It's in your future, and there's not much that you can do about it. And in fact, many people say, you cannot get out. Many people visualize, just trying with my thrusters to get out, but I'm being pulled in. The reason you cannot get out is because going back in the r coordinate, is going back to the past. So what you call outside, when you were outside, you call something the outside and the inside. But after you cross, that's not called that. That's called the past and the future. So the outside of the black hole is the past. And the reason you cannot get out is because you cannot have a time machine that takes you out. Well, maybe if you violate energy conditions and you're really clever, if you can invent a time machine that will take you to the past inside a black hole, then you would get out. You would be able to get out with it. That is pretty weird. And it's kind of cool because it's consistent. Remember, for Bob, Alice takes an infinite amount of time to get in, but for Alice it's finite time. So of course, Alice, if Alice is receiving light from Bob all the time, Alice will see all the light that Bob emitted if all the light that Bob emitted actually hits the trajectory of Alice. So it makes sense, an infinite amount of time happened for Bob, but a finite amount of time happened for Alice. So Alice cannot go back outside because outside is not outside anymore, it's the past. There's this swap between what we call space and time, and that happens when you cross this surface. R equals 2gm, the Schwarzschild radius. Now, what's going on at the horizon, now that we've understood that? The horizon, and we call it a horizon, because at that point, the trajectories of lights, the trajectories of any light-like trajectory at that point would be warped so much that all of them fall into the horizon. The event horizon of a Schwarzschild black hole is actually the point at which the trajectories of all light-like trajectories warped enough to actually fall into the inside area of the black hole. And therefore, if all the light-like trajectories fall there, like you have the light cones like that, and the light cone as seen from infinity, they're going to start being like this, like this, like that, and at some point the light cones are going to be horizontal as they cross the horizon. So the light cones if the light cones are infinity look like that, right? Then close to the horizon, they would so this is the future and this is the past. Close to the horizon, for somebody at infinity, they're going to look like this, like that, right? And then this is like this thing switch so much. So this is the outside. So this is the outside is the past and the inside is the future. So the light cones, everything points inside, and that's the surface at which that happened. All the light-like trajectories will actually fall into the horizon. And that is what's going on at horizon crossing. Now, several misconceptions that are often said in popular culture, and they're not always justified. Maybe sometimes they are, sometimes they're not, and sometimes they're just not justified at all. Number one, if you get close to the event horizon of a black hole, you'll be spaghettified. You will hear that. Spaghettified meaning that tidal forces, you see your feet would be pulled stronger than your head, and therefore you would be stretched and made spaghetti. That could happen with small black holes, but huge black holes won't do that to you. The larger the black hole, the smaller the surface gravity of the black hole. The larger the black hole, the more boring they become, in the sense that the less radical the effects would be. Now, a very large black hole, you would cross it. If you want to think of a galactic black hole, you would cross it, and then you feel nothing when you cross the horizon. Actually, in fact, you would not stop seeing. So it's interesting because maybe in class, in the live session, we can do a bit of a visualization of what it looks like to fall into a black hole. I can show you slides and some video. But basically, you will be seeing the black hole as you will see the gravitational disturbance of a black hole, and then kind of like black sphere in a way. And as you get close, it's not that the horizon doesn't get any closer for you. You will still see what you would call the horizon as you fall will always be in front of you. You would never see leaving the horizon. Even when you have crossed the horizon, you will still see as if the horizon is in front of you. And then eventually everything will become very similar to flat space-time, but then like a contracting universe. So being inside, hitting the singularity, you can think about it, right? If the singularity is in your future and all trajectories will end up there, this would look a lot like the opposite of inflation. Like all the trajectories of everything converging to a point in the future, the singularity is in the future, and therefore all you see is a contracting universe. That's what happens. Now, if the black hole is really massive, you may have quite some time to be inside the black hole. For the largest astrophysical black hole that we know, you will be able to spend several days inside. And you look pretty much like this. Actually, it's interesting because if you compute the Schwarzschild radius of the observable universe, you get the Hubble length, more or less. So it makes sense that you could think of kind of. I mean, there are caveats. There are things. This is not a precise statement, and we can discuss that. But it could be thinkable that we're inside a black hole or a white hole if it's expanding, the opposite, the time reversal of a black hole. Now, we will discuss, and I'm hoping that this will generate a lot of discussion for the live session. There are many things to talk about when we talk about black holes. One of the ways in which I could go off and I could discuss in the live session is something called black hole thermodynamics. It's what Stephen Hawking found out, that if Stephen Hawking thought of the laws of black hole mechanics, so what happens when you increase the mass of a black hole, what happens with the different laws of mechanics of black hole, and then Hawking realized that they look a lot like the laws of thermodynamics. And in a way, surface gravity played the role of temperature, and the mass of the black hole played the role of internal energy. And well, if only there was a way to relate the two, but you can't, because dimensional analysis tells you that you need a constant that has units of action and of angular momentum. What kind of constant is that? Well, that's Planck's constant. And if you actually dimensional analysis put Planck constants in the laws of black hole dynamics, you get the laws of thermodynamics. And in fact, realistic black holes, this is a Schwarzschild black hole that is an eternal black hole, but a realistic black hole would, even if it didn't have angular momentum like this one, it would evaporate in time, because black holes emit thermal radiation. Black holes are funny because the smaller the black hole, the faster they evaporate, the hotter they are. There is indeed actually a question that is often answered wrong, and I think in the What If page of Randall Munro, by the way, totally recommend Randall Munro. He's the author of XKCD, an amazing comic strip, and also he has a website and a book called What If, where he analyzes. It's a masterful mind in analyzing physics in a recreational way. And one of the problems he considers, I remember, I may be misremembering this, so please feel free to call on my BS if this is not true. But I do have that recollection. He was talking about, one of the what ifs was what would happen if the moon became a black hole. And then say, okay, let's answer with without quantum mechanics first, and then with quantum mechanics. Without quantum mechanics, it will be pretty boring, because the lunar black hole will have a Schwarzschild radius that is tiny, tiny, tiny. You would not be able to resolve it with the eye. Even when it's in front of the sun, you would not see much, even with powerful telescopes. Okay, because the gravity would be the same, of course. All right, now you switch on quantum mechanics, what would happen in that case? And then Randall Munro says, oh, in that case, the moon would start evaporating, and actually the evaporation time is around 15 minutes. So you would think that that amount of evaporation, that amount of energy released in 15 minutes would be really bad. However, he says that the temperature of a lunar black hole, or lunar-sized black hole, lunar mass black hole, would be comparable to the temperature of the cosmic background. And it's true, it's very, very similar actually, the cosmic background. And therefore, the black hole will be at equilibrium with the cosmic background, right? And therefore it would not, the amount of energy that comes in through the thermal radiation of the cosmic background would be the same that comes out through the Hawking radiation of the black hole. However, black holes have negative heat capacity. That means that when a black hole evaporates, the mass of the black hole is reduced and the temperature of the black hole increases. And that makes it that the smaller it becomes, the hotter it becomes. So fluctuations would actually make the black hole enter a runaway effect and evaporate faster. So imagine you're in equilibrium with the cosmic background, but of course equilibrium is talking about averages. On average, there's no energy exchange. At some point, the black hole would catch a negative fluctuation in which the temperature of the background is perceived as being a little bit smaller, a fluctuation in temperature. When that happens, the black hole will evaporate more. But when it evaporates more, the temperature increases. And as it increases, now it's no longer at equilibrium with the cosmic background. And it will start emitting more, but then the mass decreases, then the temperature increases even more. So actually the typical time of destabilization of a lunar mass black hole would be of the order of 10 minutes as well. So yeah, that lunar black hole would go off. And trust me, releasing MC squared, where m is the mass of the moon, at that distance in 15 minutes, I wouldn't like to be on Earth when that happened. So yeah, it would not be a good idea to make the moon a black hole suddenly. Now, I may be misremembering, and my apologies to Randall Munro if I am. So another way in which we can go off track with black holes is start talking about what is the effect of having rotating black holes or charged and rotating black holes. They become really interesting. And I actually prefer if we discuss them in the live sessions, because rotating black holes, well, one thing I can tell you about is about the Penrose process. Rotating black holes have areas that let's call ergoregions. You will hear ergospheres, but in general, in space-time, when you have regions like that, are ergoregions. What are those? This is related with inertial dragging. If you have a rotating mass, that rotating mass is going to drag space-time around it. And, if something is rotating here, it's going to kind of drag you to rotate as well. Because it's kind of dragging, it's called inertial dragging. It's dragging the people, dragging the reference frames that you place around. Now, of course, you can have propulsion, you can have thrusters and compensate for that and remain there. But it could be the case that the inertial dragging is so strong that there's no way to remain stationary anymore, not even with the most powerful thrusters. When that happens, we have ergoregions. In those regions, you cannot remain stationary anymore. And those regions can, in a rotating black hole, can actually be used to suck energy from the black hole. You can actually dump, you can have phenomena like you have the black hole, and let's say this is the ergoregion, and you can dump some particle, let's say garbage. So the garbage goes around the black hole like that, right? And maybe say that here, half of the garbage you let fall, the other half escapes. So one part falls into the black hole and the other one escapes. And you can arrange it so that the total energy of the thing that escapes is positive. So you're stealing energy from the black hole in a way. What you dropped had some sort of negative energy. There are crazy things going on, and we can talk about energy conditions inside a curved black hole. We can talk about closed time-like curves. That is the technical word for time travel. We can talk about time travel if you want, related to rotating black holes and the interesting things that happen mathematically inside the horizons of rotating black hole. You have more than one horizon, and it's very interesting. And it's something that I prefer. It goes beyond the technical level of the lectures that I want to record, but I think it goes to the exact level to have a very healthy conversation about it in the live sessions. All right, I think that's pretty much about what I wanted to tell you in terms of a video about black holes, centered, of course, in Schwarzschild black holes. I hope that you know also that Schwarzschild black holes are an idealization of black holes. This has no angular momentum or charge. Realistic black holes would have angular momentum and charge, and they radiate and they do other things. But I think this gives you a pretty cool idea of what time and space kind of look like around event horizons and with black holes. So I'm going to stop the video here, and I'll see you for the next video that's going to be about cosmology. So I will see you then, and until then, take care.